right, cool. We're off and running. All right, well, cool. Thanks for being here. Um, so let's start with any final questions on PA4. PA4 is due in the morning. Um, and then let's talk about service learning project, and then we're gonna switch gears and continue talking about dynamic programming. So any questions up front on PA4?
I had some, and then I went and looked at your lecture A, delete,
Okay.
for yesterday, and it made things a lot clearer. I've rewrote it like 4 times,
Okay.
and I've gotten it to the point where it preserves the binary tree structure.
Mm-hmm.
Not exactly what we're looking for. And I have to ask you, are we going about this to best preserve balance?
No. We're not really doing anything with regard to balance.
Okay.
The algorithm that I'm asking people to use, replacing the root with the largest node from the left subtree, I'm picking a particular algorithm because the only way I can know if you implemented an algorithm correctly is to compare your output to what I expect the output to be. And if some people are, using the smallest node on the right, and some people are doing something else, and some people are balancing and so on, when I run your code and I try loading in some data and deleting some data, I'm not going to have any way to know if your delete algorithm is doing the right thing unless I reverse engineer your code. So I'm standardizing the algorithm that everybody's going to use, and then I can predict what the tree should look like after I make certain deletions to it. That's the only reason I'm insisting on that particular algorithm. Let's see. Do you want us to call search inside delete? So delete does not have any way to return a success or a failure, and so I suggest you call search inside main. So when the main program says, okay, the person's trying to delete a plate, have your main program call search, see if that plate exists. If it's not in the tree, then main can print a message saying, that doesn't exist in the tree, plate not found. If it does exist, then main can go ahead and call delete, and then your delete function doesn't have to worry about is this in the tree or not. You can just assume it's in the tree because main won't call delete otherwise. And again, we don't want delete, to do things like print error messages or things like that, so those would have to come from main as well. Let's see, can we go over LRN? Absolutely. So here's a tree, and we want to traverse it in left-right node order. So we want to do 3 things. Our goal is to print everything in the tree, but the order in which we're going to print them is the following. First, we're going to print everything to the left of the root, and then we're going to print everything to the right of the root, and then we're going to print the root itself. That's what we mean by LRN, which is also called post order. So pre, post, in order refer to the position of where we print the root node. We're printing the root node after everything else, so that's the post part. So how do we print the stuff to the left of the root? Just call LRN on root arrow left, and that will take care of the entire left side of the tree. And then we need to next print everything in the right subtree, so just call LRN root arrow right, and that will print out all of this stuff. And now the only thing left to print is the actual root node data, and so this is just a printf, and just print root arrow plate, root arrow first name, last name, and so on and so forth. And so that's almost your complete LRN function. What's the one thing we need to add here to keep things from segfaulting?
A print or something to go through it?
Besides that, one other thing that we're always going to have near the beginning of our recursive functions, there's a general kind of statement. Say again?
If null.
Yeah, something that ends the recursion, because this says, let's call ourselves on this subtree, and as it is, we would just keep calling ourselves over and over and moving further and further to the left. If that goes forever, we're going to run out of memory. But in reality, once we get down to the last node and the left subtree doesn't exist, it's null, we're going to call this with an argument of null, and then this would segfault. So we have an if statement in the beginning which says, if root equals null, then return. So I'm assuming we're traversing a tree with a root that we're calling root. So this is like the base case in induction. This is what stops us from just infinitely going down the rabbit hole and never coming back up. This tells us, okay, we don't have to do any work because printing the contents of an empty tree, just don't print anything. But in all other cases, if there's anything in the tree, we print using these recursive steps. Dump out everything to the left, everything to the right, and then print the root node data. So that's
interesting you bring that up, because if I had been thinking about this in terms of like induction, this might be a little bit easier to
okay.
at first. But it's a phase case, you have to have a stopping phase.
Yeah, and they do go together. And one way in which they go together is if you wanted to prove that this would do the correct traversal, you could write an inductive proof for it using mathematical induction. And your base case would be, let's suppose that a tree of height -1, that this works correctly. And we can immediately verify that that's true, because if the height of the tree is -1, the tree is null, the root is null, it'll return, it won't print anything, that's the right thing to do. And now you just have to show that if this works for a tree with a certain height, it'll work for a tree that's one level higher. A tree with a deepest node one level deeper. And you'll be able to do that because each of these will, root left and root right will be a tree of height, n. And so if this works and this works, then the algorithm on the tree of height n+1 will also work. So yeah, that all kind of ties together. What's the technical CS term for the recursive terminating condition again? I don't know. I've been calling it a base case, but I don't think that's standard terminology. That's like reference to the induction. I don't know if there's probably a name for that, but I don't know what it is. It's the thing, yeah, it's like a stop sign. It's the thing that stops it from blowing up. Yeah. I mean, I'm okay with calling it a base case. Because really what we're doing is, like with Fibonacci numbers, right? When we write a recursive formula for Fibonacci numbers, we're defining, two possibilities. If n is 1 or 2, the Fibonacci number is 1. Otherwise, it's the sum of the two previous. And this is, kind of like a base case. And that's really what's happening here. If we wrote the definition for doing an LRN traversal, it would be, do these things if the root is not null, do this thing if the root is null. But if someone finds a more official name for it, let us know. All right, good. Other questions?
For 5 minutes.
Say again?
I think I fished around looking for that for about 5 minutes and couldn't find it.
Oh, okay. Maybe it has no name. Maybe it's waiting for a name. All right, other questions? All right, cool. All right, so couple of announcements on service learning projects. So first of all, remember your SLP poster is due Monday morning at 8. It's a PDF that you download from Canvas, fill in the parts and pieces to reflect, your progress this quarter on the SLP, and then upload it as a PDF. That's got to be uploaded by 8 a.m. on the 28th, which is Monday. So don't.
Quick question on that poster.
Yeah.
So you guys have a section I'm looking at right now for competitive analysis, competitor pros and cons. So if you're making a game, what is that directly referring to? Because I get it, like if you're building something that someone else might also be building, there's pros and cons there, but what is that directly referring to?
Well, there's other games out there, right? There's tons of games available, and so you're making a game. So how does the game that you're making compare to other games that are out there? And it's a very open-ended question, right? You could, if you're making, say, a side scroller, you could compare yourself to other side scrollers, or you could say, this is a game that runs on a phone. How does it compare to other phone games? Or it's a PC game. How does it compare to other PC games? Or how does it compare to other ways that people relax and decompress after being at school or work all day, if that's, what you're saying is one of the things that this game is for. So it's just kind of thinking about, you're working on a project. We're not expecting you to come up with, a completely original, never before dreamed of creation for your service learning project. But put on your marketing hat, right, and just kind of think about it in terms of, if you were trying to present this as, this is something different, this is somehow unique from other things, what would you say about it? So it's just trying to get you to think in those directions, basically.
So holographic full immersion, that's probably a bit out there.
That would be out there, yeah.
A little bit ambitious.
Yep, but that would be super cool.
Ours is a little done before, but it's usually not something you do with the engine we're using.
Okay.
Like a server authoritative architecture.
Oh, cool. Okay, yeah, that sounds awesome. So yeah, here's the poster, right? Please at least, put in your actual project title, replace the word date with the date, and, put in something close to the actual date. Instead of, like September 21 or something like that. And if you have a name for your team, go ahead and put it there, and list the actual names of the team members, not the word team members, right? Spend a little bit of time on this, because they get these things and they'll have a project title of literally project title, and it's
what if it's a working title?
That's fine.
To change, just put like working title and then this, or just put the title in.
I would just put the title in there. I mean, if you really feel like you don't want people to think this is what it's actually called, you could put the title in and say parentheses, working title or something like that. Thank you.
You're welcome. We are presenting this and the project sometime in the next couple of weeks, right?
Yeah, so that's the other announcement. Presentations will be on Tuesday, March 8th, and that's from 3 o'clock to 5 o'clock, and it's going to be virtual, so it'll be a Zoom meeting. And it'll be both sections of 222 plus Izad's Engineering 252 class. So all of the final year engineering computer science students will present their projects, and it'll be one big Zoom room. And we'll put people into breakout rooms, probably about 4 people per room, and you'll just basically round robin, do your presentation, and then the next person will present, and you'll just kind of do that. And different people will come by during that time and pop into different rooms. We'll have a list of topics on the Zoom page that people can come by and say, oh, this person is working on a cool sounding game. I want to see what they're doing. So they'll hop into whatever room you're in, and when it's your turn to present, you'll just kind of talk about it. And the presentation can be pretty much anything that you think helps explain what you're doing and where you are, that kind of thing. So if you have some kind of prototype of a system you're developing, you can certainly show that. If you're still, you know, trying to work out the details and start developing a first version, right, you can talk around your poster, right? You can put this up and you know, describe what's going on in these different sections and so on. If your project is to make a website, and you've completed it, you can show the website, right, and talk about what you did and so on and so forth. Also, you know, you definitely want to talk about what your plans are for the remaining quarter. So it's just kind of a general, you know, what we call a dog and pony show, and it's a typical kind of thing that you'll find at trade shows and technical conferences and so on and so forth. Our poster sessions. That's basically what this is. Unfortunately, it's still being done, you know, virtually, but in an in-person format, there's typically a room, and it's filled with people, and there's posters, you know, attached to the walls, and people will come by and just walk around, look at the posters. If they see something interesting, they might come up and start talking to you about it, asking you questions, and so on. And, you know, if your project is not finished, that's totally okay. We don't expect you to have, you know, kind of a final prototype here. If you've made, you know, some progress on it, that's what you can talk about. If there's some, you know, something you can show from that progress, you can show that. If you don't have anything to actually show, you can talk about, you know, where you are, what your plans are, how far you've gotten, what difficulties you run into, what you're going to do to get past those difficulties, and so on. So it's understood that, you know, this is not a final presentation for the entire year. And even in June, you know, when the SLPs are done, you may not have a working prototype. It depends what you're doing, how many issues you ran into, and so on. But if you've been working on this, right, you've theoretically spent probably 25 weeks now working on this project. There should be, you know, 5 or 10 minutes worth of stuff you can tell people about that. So think about, you know, where am I on this project? What do I want to tell people about it? That kind of thing.
So you're saying, like, even if you get into it, you have some stuff, but it's not a full, complete, everything that you dreamed it would be.
Mm-hmm.
You know, it's still okay.
So if you're trying to build, you know, an automatic bird feeder, it's great if you succeed and you've got an automatic bird feeder, but the real goal is, you know, the process of trying to do that, the learning that takes place. Hey, I figured out, you know, how to use a servo, and I found out servers blow up really quickly if you don't put resistors in parallel with them, you know. And so there's all this learning that takes place in the process of trying to do your project. And it's definitely not just about, you know, here's my project, I'm done. It's what have you learned, right? Hey, you know, it's a lot harder to work on a project when I don't have weekly goals. You know, if I only set up like 2 milestones, I found I didn't really do a lot of work until I got to, you know, right before the milestone, or maybe I didn't do any work until the week before the quarter ended, you know. And so are you learning about how to schedule your time? Are you learning about how to choose what the scope of a project should be, how to measure where you are in a project? All of that is like really, really valuable learning, and that's the stuff that is going to be so powerful when you're in a job interview and someone's trying to decide, should I hire you or this other person, right? All of this experience that you get from doing something like a service learning project, that's all dynamite. That's stuff that can make you so attractive to a potential employer. And so you know, everything that you're doing and learning and experiencing, including, you know, any setbacks or things like that, that's all like positive experience. And so you can definitely talk about that. Some pieces on the poster itself, right? Problem definition is you know, the who, what, when, where, why of the project itself, right? What are you trying to do? I'm trying to build an automatic bird feeder. What's the scope of that? You know, Am I actually going to build it, or am I just coming up with a design for it, or am I just coming up with a software control system for it and simulating what it would do? And the schedule, the milestones, how far you plan to get by certain points, resources, right? What do you need? I need somebody who's an expert in bird feeders, or someone who's an expert with mechanical engineering, you know, or I need a bird that will help me test my bird feeder, right? So what are the resources you need? And then, as we said in the beginning, competitive analysis, right? So, you know, how does this compare to what's out there? Just kind of thinking about, you know, pros and cons, advantages, disadvantages, things like that. Potential applications, what do you see this being used for? This is partially, you know, an exercise in changing hats, right? We're engineers, we're computer scientists, but, you know, sometimes we need to be marketing people, sometimes we need to be advertising people, sometimes we need to be business people. So this is a chance to sort of play around with that. So imagine that you're trying to describe, you know, what your project could be used for. Have fun with this, right? Let yourself be creative and get a little crazy if you want. Future improvement ideas, right? You're not committing to do these things, but, you know, if somebody said, wow, this is a brilliant idea, here's $1 million, go start a company, you know, what could you do with this project? Where could you take it? And then, you know, the other half of this roughly is, you know, if you've been working on this and you've started to make some progress towards a solution, what have you figured out? So this can be code, it can be block diagrams, it can be, you know, schematics, it can be pseudocode, it can be, you know, whatever you've got sketched out on the back of a napkin or on a whiteboard or on paper to you know, illustrate your current state of development of the project. And yeah, someone asked in terms of job interviews and stuff, it's not just SLPs. If you have personal projects you're working on, same idea when you get to, you know, tell me about yourself or tell me what you did when you were in school. You know, anything that you're working on that shows, you know, creativity, initiative, organizational skills, follow through, discipline, time management, those kinds of things, right? Those are all really valuable trademarks, characteristics. And so, you know, if you're just, you know, making a game for fun, or you're trying to wire up your bedroom to respond to voice commands, you know, or whatever, that's all like really good stuff. And typically, you know, the most valuable learning people get out of school is from the projects they do. And sometimes it's projects that are assigned in classes. A lot of times it's just projects people are working on. All right, cool. Any other questions on that?
I actually have another question on PN4.
Yeah.
If you don't mind.
Go for it.
When we're talking about closing the file after it's been read, is this something that happens in the exit command, or is this something after it's been read and it's completely and it's already been used?
I would just close it as soon as you finish reading it.
Okay.
So let me see. So, you know, check your arguments, make sure you've been given an argument, which is a file name. Ingest the file, which is, you know, open, read, add, and then at the end of all that, go ahead and close the file. Then you don't have to worry about it. And then, you know, main loop, which is, you know, read a command, process. And just keep doing that. And then your exit, which is basically, you know, free memory. And then maybe say goodbye. And then just exit. The only downside if you don't close your file is you'll get a memory leak. And it'll be like some suspicious 56 bytes or something at the end that it says are still in use. That's just...
I found that out the hard way.
Yeah. So calling F
Yeah,
closed.
that's the worst when you're like, yeah, I'm done. And then you run it through Valgrind, and then you realize you're not done.
Right, right. Yep.
I think that was the worst with PA3 because we'd done the freeing of the nodes in the linked list, but we had never freed like individual elements. You know?
Oh, yeah, yeah, yeah.
And so I was like, what the heck is going on? It's not freeing. And come to find out, that's what it was.
That was
Yep.
missing there.
Yeah. I had never heard of that before, never done it before, so. It was
Yeah,
just-
I'd forgotten about that, and some people asked about it. I was like, huh, that's really weird.
Yeah.
All right, so let's go back to dynamic programming. And we played around with some Fibonacci code last time, and we saw that writing a recursive Fibonacci function is very simple to write and very slow to execute. And it was slow primarily because as we try to calculate a Fibonacci number, we keep having to calculate all these other Fibonacci numbers. And the tree of the number of times we have to call our Fibonacci function grows at about the same rate as the Fibonacci numbers themselves grow. And so to calculate the 100th Fibonacci number requires, you know, some ridiculous gazillion number of calls to our Fibonacci function. And so we introduced this concept of dynamic programming, which basically said, hey, once I've calculated a certain value of the Fibonacci function, I'm going to save that value in memory. And later on, if I find I'm trying to calculate a value I've already calculated, I'm not going to do all of that recursion. I'm just going to read the saved value out of memory and prune that part of my recursion tree. And so we can take this problem that involved a lot of recursive calls and change it into one that has very few recursive calls. And dynamic programming is just this notion of saving those values in memory and then reading the values out of memory instead of recursing.
I have to wonder. I've been thinking about this since Tuesday.
Mm-hmm.
You mentioned it. If you were to cache it, you would probably get pretty similar performance to like the non-recursive call, right?
Yes.
That's
And
crazy.
it depends on the particular function. So for Fibonacci series, you don't actually recurse all that deeply. And so the overhead of, you know, doing a function call is pretty minimal. For some of these other ones, there could be a bigger difference. But for some of these functions, trying to do it non-recursively is going to be extremely difficult. And the recursive way is going to be kind of the only way to go, realistically. And so,
I feel like
yeah, go ahead.
Your next assignment might be like PA4, but we're gonna cache addresses of nodes, right?
Yeah, your next assignment's going to be the knapsack problem, which is going to be our next example of dynamic programming, and is an example of a problem that if you don't do it recursively, it's pretty difficult to see how to do this. But with recursion, it's pretty straightforward, but very inefficient. And so recursion plus dynamic programming will get a very efficient algorithm. And so here's a an example of a nice recursive problem. So this is the knapsack problem. And there's a number of different knapsack problems. It's a general class of problems. But they're all kind of the same idea, which is you have some kind of container, a knapsack or a bag, right? And it can hold a certain amount of stuff. And typically we measure that by a certain amount of weight rather than volume. So we have a bag that can hold, say, 20 pounds of stuff. And you're allowed to put anything in the bag that you want as long as the total weight of things in the bag doesn't exceed 20 pounds. And you have a list of items, and for each item you know its weight and you know how much it's worth. And your goal is to fill your bag with as much stuff as possible so that you maximize the dollar value of what's in your bag. So this is like, the Home Depot shopping spree. And they give you a bag and you can fill it with whatever you want. So what do you put in your bag, right? Do you fill it up with nails or power tools or gift cards, right? And probably $100 gift cards would be your best bet. But they always exclude those from these promotions. So we have some sort of inventory table with a list of items and weights and values. And in some cases, there's limits on how much of this stuff is available. In some cases, it's an unlimited amount of everything. So it's an infinite Home Depot, right? Never runs out. Another distinction is that in some cases, you're allowed to take fractional amounts of items. For example, if this was, if there was a bulk bin of oatmeal, you don't have to buy, 1 box of oatmeal or 2 boxes of oatmeal. You could take, 2.356 ounces of oatmeal if you wanted, because it's, in a big bin with a scoop, and you can just measure out how much you want. So we're going to do a problem which is an integer knapsack problem, and it's unlimited in the sense that there's an unlimited amount of each of these items available. But this is going to be the integer knapsack problem. It's sometimes called the 0-1 knapsack problem, because you take an item or you don't take it. You're not allowed to take fractional amounts. And so here's what this might look like. Let's imagine an inventory of 3 items. So our first item is going to be a book. And our book weighs, I don't know, let's say I'm going to use pounds, but it doesn't matter what the units are. It's going to weigh 2 pounds, and maybe it's worth $1. All right. And then the second item will be, what's a good second item here? Oh, I don't know. It'll be a phone. And the phone weighs 3 pounds, and that costs $9. Because, phones are pretty cheap these days. And the last item's going to be, like a tablet. And that weighs 4 pounds, and it costs $13. And what you're told is what the capacity of your bag is. So let's suppose the capacity is 10 pounds. And the question is, what combination of items, right? You've got an unlimited number of these available. What combination of items should you fill your bag with in order to maximize the dollar value in that bag? So I could do 2 tablets and a book. I could do 3 phones and have a pound left over. I could do a tablet and a phone and a book. I could do a tablet and 3 books. I could do 5 books, right? There's lots of different combinations. And so the knapsack problem asks the question, what combination of these items, how many of each item will maximize the value of what's in the bag?
Probably the most tablets you can get without going over 20 pounds.
Yeah, so
from there, fill in the gaps of how much weight you have left if you can't fit in a form of a tablet.
So if we calculate the value of each item per unit weight, right? The book is not worth a whole lot. It's worth, 0.5 per pound. The phone, on the other hand, is worth $3 per pound, and the tablet is worth 3.25 per pound. So per pound, this is the most valuable item, this is the next most valuable, this is the least valuable. And so one approach to this would be, hey, let's put in as much of the most valuable item as we can. So we would say, let's take 2 tablets. That's 8 pounds. And the value would be 2 times 13 would be $26. We've got 2 pounds left. We can put in a book, which is 2 pounds. And the value of that would be, one book at $1 is $1, and this ends up being $27 we get in our bag. So is that the best solution?
I would think it would be, well, no, that's not the best solution.
I think it would be, because you went and you got the most of the best value per weight as you could manage within the range, and then you build in the rest with the next best.
No, you'll get 50 cents more if you get 3 phones and a book. You'd be at $27.50.
3 phones and a book won't fit though, because that would be 11 pounds.
Oh, the book's 2, that's right.
The book's 2, but I like the way you're thinking.
So that... Now, if you got 1 tablet and 2 phones, that'd be 10, but then you're looking at, that'd be like 31, isn't it? Because it'd be 18 plus 13.
So 2 phones would be another 6 pounds, and those are worth $9 each, so 2 times 9 is 18. You got 31 pounds in your bag, right? 10 pounds, but you got an extra $4 out. So this is a better solution. And this is a little counterintuitive, right? Because we put 1 tablet in, well, a tablet's worth a whole lot of money, right? So we go ahead and we put a tablet in. But instead of putting a second tablet in, we had 6 pounds left, but we deliberately ignored the most valuable item and instead put in an item that was worth a little bit less. But because it also weighed less, we were able to get 2 of these in here, and 2 of these phones is worth more than 1 tablet. So here's the situation. If these were bulk items, if we could take, half a tablet, for example, we would take 2.5 tablets. $13 each. 2 times that would be 26, plus 6.5 would be $32.50. That would be our best solution. And there's times when that kind of approach will work. All right, that's called a greedy algorithm. A greedy algorithm is one where you try to find the best solution to your problem right now. You're not thinking about tomorrow, you're not planning for retirement. Give me the money right now. Okay, it's a greedy approach. And in some cases, greedy algorithms work really, really well. For example, if we're allowed fractions of these items, yeah, absolutely, find the most valuable item, take as much of that as you can. If you run out of that item, find the next most valuable item, take as much of that as you can. And keep doing that. For the integer knapsack problem, though, greedy approach does not work. Here's a counterexample. And this is similar to problems in graph theory, right? When you, let's say you have a graph, and you're trying to find the shortest distance from A to B, and this is 2 miles, and this is 3 miles, and this is 10 miles, and this is 1 mile, and this is 20 miles, and this is 30 miles, and this is 50 miles, and this is 17 miles, right? Starting from point A, the shortest distance would be right here. The next shortest distance would be right here. A greedy algorithm for finding a path from A to B would say, hey, let's go down the shortest distance, that's here, and then let's find the shortest distance from here, and then the shortest distance from there. But in fact, if you go from A to here along this path, which has length 10, which is a really long length compared to 2 and 3, you only have to go one more, you can get from A to B in a total distance of 11. Whereas if I go here, my distance is going to be something like 20, and if I go here, it's going to be something like 21. Or actually worse than that, like 54. So sometimes greedy algorithms work, sometimes they don't. And the knapsack problem with integer values, greedy doesn't work. Let's see, someone asked, could you frame the problem negatively? What should I not take? That's an interesting question. I'm not sure that works either. I don't have a handy counterexample for that, but I think that I think that would be another version of a greedy algorithm.
It seems like you could. The inefficient thing to do here would be like one of those combinatorial problems from 215, where you need to like find every possible combination and see what's the greatest. But that would be kind of a waste, right?
Yeah. So this is another version. You can do an exhaustive approach, and it's trivial to code, right? Just take every possible combination of these. Take everything from 0 up to 5 books, 0 up to 3 phones, 0 up to 2 tablets. So 3 nested for loops, and for each one, calculate the value that you get out of it and just record the maximum. That's pretty straightforward to code, but it takes a lot of calculations. If you had 100 items to pick from, you'd have 100 nested loops. And the amount of time it would take would be prohibitive, most likely. So this is our setup. And we're only allowed to take integer numbers of things. All of these values and weights are positive. If we had an item with negative weight, the problem is unsolvable. Right? If I had something that had negative weight, I could put a bunch of that in my bag, and then I could add a bunch of weight to offset that. And once my bag reached 10 pounds, I could add some more negative weight, some more helium balloons or something, and then add some more stuff to it. And basically, there's no limit to how much stuff I could put in my bag then. So this problem, positive weights, positive values. And so, not surprisingly, given where we are in the course, we're going to look at a recursive solution to this. And the recursive solution if you follow along with it, it's a pretty simple solution. But implementing it has lots of technical difficulties. And this is going to be part of what PA5 is about, is addressing these technical difficulties. But play along as we go through this, and don't get too bogged down yet on the implementation aspects. Let's look at this from kind of a higher level of an algorithm. And then we'll start working through some specific examples. And I've got some cool worksheets we're going to fill out to do that. And then we'll move into talking about the actual code after that. So here's the basic setup. We're trying to write a function. And this function, I'm going to call it maxval for maximum value. And maxval is going to take an argument, which is an integer called capacity. And it's going to return an integer, which is the maximum value I can get from a bag with this capacity. So for example, if this is my list of items, my inventory, and I called maxval of 10, I would like my function to return 31. If I called maxval of 4, I should probably return a 13. If I call max val of 1, I should return a 0, because if my bag only has a capacity of 1, none of my items fit in it. And so how much stuff can I put in a bag that only holds 1 pound? Nothing. So the value I would get out of that would be 0. So we want to design a function called maximum value. Takes a capacity, returns the most value you can put into that bag. And most of these problems we're going to talk about today and Tuesday work with the following observation. We're trying to choose which items to put in our bag in order to maximize the value. There's going to be some item we put in first. It's going to be a book or a phone or a tablet. We know we want to put something in our bag. And it's going to be a phone, a book, or a tablet. And really, the order in which we put these things in the bag makes no difference, right? There's no sort of stacking going on or anything like that. But if we look at the process, you know, this person filled their bag and got a really good value out of it. There was some item they began with. And since there's 3 items in our inventory, there's only 3 possibilities. They might have started by putting in a phone, or a book, or a tablet. And that's it. Those are the only 3 possibilities. So let's explore what happens in each of those cases. So case 1. Put a book into the bag. Now we don't know if this is going to get us the maximum value out of the bag or not. In fact, we kind of know from peeking ahead that if our capacity is 10, our best answer is going to be from not putting any books in. We're going to put in 2 phones and a tablet. But, you know, there's 3 possibilities. We're going to start by either putting in a book, a phone, or a tablet. So one possibility, we're going to put a book into the bag. All right, if we put a book into the bag, how much money do we have in the bag right now? What's the total value of stuff we have in the bag?
Just 1, right?
It's just 1. It's $1. We've put 1 book in the bag. The book weighs 2 pounds. Our bag holds 10 pounds. Once we put the book in, how much space do we have left in the bag?
8.
We have 8 left, right? We have 10 minus 8. 10 minus 2, that's 8 pounds of capacity left in the bag. All right, here's a loaded question. What's the maximum amount of stuff we can get out of a bag whose capacity is 8?
Any idea?
Oh, you might disconnect.
Oh, I might just disconnected. That's weird. Hold on.
To answer your question, I think 26.
Alright, hold on a sec.
All right, I think I'm back.
You're good now.
Awesome. All right, did I kill my recording? Nope, my recording's still good. All right, let me go back to that. All right. So so you said 26, but that's because we're smart and we can go through and we can do this calculation. But we don't know ahead of time that the maximum value we can get out of an 8-pound bag is 26. Right? You and I can see 2 tablets gets us 26. But is there some other way we can describe the maximum value we can get out of a bag with this capacity? And think about recursion. Do we have a function that can tell us the maximum value that we can get from a bag of a certain capacity?
Would you just call max val again with a
Hey.
capacity of 8?
Nice. Right?
So
This
would you
is
just do capacity minus,
the weight of this item.
I guess, the weight, yeah.
Yep.
Okay.
So the value we get if we put a book in our phone is the value of the book plus whatever we can get out of this slightly diminished capacity bag. This bag that now holds only 8 pounds. How much can we get from that? Well, our max val function will tell us that. So that's case 1. Case 2, we start with a phone, in which case the best value we can get out would be the value of the phone, which is 9, plus whatever the most value is that we can get out of a bag that originally held 10 pounds, but we've used up 3 pounds for the phone, so a bag that can hold 7 pounds, right? The maximum value from that plus 9, that's what we can get if we start with a phone.
So is this just high-level pseudocode, or are you saying we should actually do this as a switch statement?
This is just pseudocode. Yeah, I don't mean a case statement. So third case, we have a tablet. And in that case, the maximum value we can get would be the value of the tablet plus whatever the maximum value is that we can get from a bag that now holds only 6 pounds because the tablet took up 4 pounds out of our 10. So if we calculate these 3 expressions and we pick the largest, that's what we should return from our max val 10 function. And so this is, you know, a classic recursive algorithm now. How do we calculate max val of 8? Well, we'll do the same kind of analysis. And how do we calculate max val of 7 and max val of 4? Same kind of analysis.
For the third case, it should be 10 minus 4, right? It should be 6.
Yeah, 10 minus 4, thank you.
So I know we'll probably get to this, but what exactly are you evaluating? Like, is this going to be an if statement or like an else if kind of thing? And
It could be anything that gets us there. So it will probably be a series of if statements inside a loop. But the effect is, right, for each item in the bag, we want to calculate the maximum value we can get by putting that item into our bag. And then pick the largest of those 3. That tells us which item we should start with, and it also tells us what the maximum value is that we can get. And so to pseudocode this a little further, max val of some capacity. So for, let's just iterate over each of the items. So let me call this item 0. So let me add an item number. So this will be item 0, item 1, and item 2. So you'd have, like parallel arrays or something like that, an array of weights, an array of values, an array of items. We don't need value per weight. That was just an illustration that greediness doesn't work. But we have arrays storing this information. And so, for example, if you have a total of 3 items in your inventory, we're going to want to loop over those for I equals 0 to 2. And, I'll start off with something like best value equals 0. So, this is best value so far. And so this value, if we start with item 0 in our bag, what's the value we get from that? Well, it's the value of item I. So I'm assuming these are arrays. So it's the value of item I plus the most value you can get from a bag whose capacity has been reduced by the weight of item I. And if this value is bigger than the best value we've seen, then just save best equals this value.
So when you're reading in the file, you should just initialize 2 arrays and one for, or I guess 3 arrays?
Yeah, it's going to be 3 arrays, one for name, one for weights, one for values.
Okay, and then just have everything for that one item stored at 0 and the next one at 1. So
Exactly.
All on it that way?
Yeah, so
Okay.
parallel arrays, right? Item 0 is the name, weight 0 is that item's weight, value 0 is that item's value. Or, you can make a structure that contains a name and a pair of integers, and then you could just have an array of those structures, because structures let us get away from parallel arrays. So there's flexibility in how you want to implement this. All right, so we can iterate over the items, and when we're done, just return the best value that you've seen. So this calculation is where all the good stuff happens, right? And again, this is saying if I start with item I in my bag, I get this much value from that item. I reduce the capacity of my bag by this much, and max val of that tells me how much value I can get out of that remaining capacity. So that remaining value plus the value of item I, that's the best value I can get if I start with item I. If that's better than the best value I've seen, let's remember it. And then at the end of going through all these items, we just return whatever the best value was we got. And there's one other minor but really critical detail here, which is when we're doing this analysis, if our bag only holds, say, 2 pounds, we can't put a tablet in our bag, and we can't put a phone in our bag. This calculation only makes sense if item I fits into our bag. And so make sure that before you do that calculation, you do something like, if the weight of item I is less than or equal to your capacity, then go ahead and do that calculation. But if item I weighs more than what your bag can hold, you cannot put item I into your bag, and so this is not a possible value you can get, and so don't, consider that to be maybe the best value. And if you run this loop and nothing fits in your bag, right, you'll never execute these statements. Well, best has been initialized to 0, so at the end you'll return 0, which is the correct thing to return, right? If no items fit in your bag, the maximum value you can get out is 0. So that'll still do the right thing even in that case. So that's pseudocode, a little closer to actual C code for how we can go about doing this. But the essence is, really just we're thinking about each possible item we can put in first. And this calculation is the value of that item plus max val of the space that's left over in the bag.
So PA5 is only going to be pretty much one function in the main program, right?
Pretty much, yeah.
Are we still doing like the make files and everything like that, or did you want?
Yeah, so I didn't put it in the PDF, but I added it on Canvas and said make sure you include a make file.
Okay, so you still want a function, a main, and a.
I'm okay if you want to do it all in one file. That's fine with me.
Okay.
Yeah, you don't need separate files, but I do want a make file just so I can say make to compile everything.
Okay, and that would, I mean, you just pretty much have one, or I guess three targets, main.o, the main target, and then a clean.
And a clean. Yep.
Okay.
Yeah. All right, so let's do a 5-minute break, and think about this a little bit. And then we'll come back and we'll go through a specific example with this and see exactly what this looks like, and also see how to keep track of the actual inventory of items that we want, so that in the end we know not just that our maximum value is, say, $31, that we know we get that from having 2 phones and 1 tablet. So we'll play through that example, and then we'll take a look at PA5. And there's not a whole lot to the assignment. It's basically writing a program to do this. So we'll come back in about 4.5 minutes and dig further into this.
accordion?
I think that's a violin.
Oh,
Violin, I think he plays it.
nice. I just came back and heard that. That's cool.
I thought he had some sweet background music. I was like, hey, he's stepping it up.
Wish I could approach music that easily. It's kind of hard.
Yeah, I'm not much of a musician either.
Oh, everyone's a musician.
Well, my dad tried hard because he was a music producer for a very long time.
Oh, wow.
Yeah, he actually more recently represented Sly and the Family Stone.
Whoa, that's cool.
Yeah, he's good friends with Sylvester Stewart or Sly.
Oh man, that's so cool.
Yeah, he was big in. We actually had Ralph Tresvant from New Edition staying at the house with us while they were developing an album.
Oh,
which
dang.
was pretty cool.
Yeah.
Yeah.
Whoa, that's like trippy.
Yeah, that's kind of fun.
Yeah.
Yeah, actually, cool little fact here, or fun fact here. So when Sly Stone was moving out of his house, he had me and my brothers come and help move him.
Oh yeah.
I got to actually play the piano or the keyboard that he played at Woodstock.
Oh man.
This is really cool.
That's like seriously awesome.
Yeah, yeah. It's history, you know.
Totally, yeah. Wow. All right, I'm gonna tell that story to some friends.
Yeah.
All right, so I have these cool inventory sheets that, you know, if we're in person, I pass these out and people work on them in groups. But where I'm just gonna do this on camera and we'll work this out as one large group. And so I'm gonna stick with this item list, right? So book, phone, tablet, 2, 3, 4 pounds, $13 value. We already know what the answer is for a capacity of 10. But let's go ahead and work through this very methodically, and also keep track of the inventory, because for PA5, you're going to want your final solution to be both the maximum capacity and the inventory. So we're going to start off, we're going to say our capacity is 10. This is our first call to the maxval function. And every time I make another call to maxval, I'm going to start another part of a sheet. And I've got a few sheets here. I don't think I have enough to do the whole thing. But I will print out a few more in the background. Let's see. Recursion sheets. Alright, hold on. Worksheets, alright. All right, so we're calling maxval with a capacity of 10. And we have 3 items, so item 1, item 2, item 3, so. All right, so if we start with item 1, the value of that is $1, and the capacity is reduced by 2 pounds, so whatever maxval of 8 returns, that plus 1 will be the value we get from starting with item 1. All right, item 2, which is a phone, the value of that is $9. The weight is 3, and so 10 minus 3 is 7. This will be 9 plus maxval of 7. And then if we start with the tablet, that has a value of 13, and it weighs 4 pounds, so the capacity was 10 minus 4. That's 6, so whatever the max value of 6 is, if we add 13, we get the best value that we can by starting with this. All right.
So,
yeah.
Doesn't this fall under the greedy algorithm?
No, because
that will fit. No, okay.
So we don't know which of these. We're going to try all 3 of these, right? And you know, we're also trying the possibility that we start with a book, which is just, you know, this really kind of half $1 per pound item, right? That's actually, you know, happens to be the first thing we're going to consider. But we're going to try all 3 of these. A greedy algorithm, we would decide definitively what's our first move going to be. based on the situation at that point. And then we've made that decision, is cast in stone, we update the problem, we make a new decision. So it's definitely not a greedy approach.
Okay.
All right, well, we need to find max val of 8. So let's go ahead and do that, and that's going to be a new sub-problem. So let's find max val of 8. And so, same drill, right? If we start with a book that has a value of 1, it weighs 2 pounds, our capacity of 8 goes down to 6. So 1 plus max val 6. If we start with item 2 that has a value of 9, weighs 3 pounds, our capacity of 8 goes down to 5. And if we start with a tablet that's worth $13, weighs 4 pounds, our capacity of 8 goes down to 4. Alright, well now I gotta find max val of 6. So let's make another call to max val, and we're calling it with an argument of 6. And these are call frames, right? When I return from here and I know max val of 8, I'll be able to complete this line, and they'll go on to the second pass through my loop and figure out 9 plus max val 7 and 13 plus max val 6, and so on. All right,
so you're individually doing a recursive for each case, basically, and that's what's returning the best value.
Mm-hmm.
Okay.
Yeah, so I'm making. Go ahead.
No, go ahead. I'm kind of thinking about it a different way.
Okay, so yeah, so I made a recursive call to max val, which down here the first time through my loop I'm going to have to make a recursive call to max val of 6. So I'm going to call max val of 6, and when I come back from that call I'll write in the value here, and then I can calculate this expression. And then I'll find max val 5, calculate this, max val 4, calculate this. I'll return the largest of that, that'll be max val 8. I can put that in here, do the same here, do the same here, and then whatever the largest is, that's my final answer. So we're...
by the end of this, you're going to go through every recursion from 10 all the way down to 1.
Not necessarily. For example, I don't think we're going to call max val 9.
Okay.
But we may hit...
Or 1.
Yeah, we may hit the others, but it depends. If my lightest item was 5 pounds, there's definitely weights that I would not calculate.
Okay.
And so I'm definitely not trying to just iterate through and calculate each max val. I'm doing it kind of on demand, right? I need max val 8 here, which means I need 6. So now I'm going to calculate max val of 6. And if that needs me to find some other max vals, I'll do those. This is a depth first process, right? I'm going deeper and deeper down. I'm going to do all this work just to find max val 8, and then I'm going to go on and do the second pass through my main for loop and do max val of 7 and so on. So this is kind of depth first, and that's classic with recursion, because recursion involves using the stack, and stacks are depth first, queues are breadth first. All right, so we're getting pretty good at this now, right? This is going to be a 1, 9, and a 13. Book weighs 2, so this will be max val 4. Phone weighs 3, this will be max val 3. And tablet weighs 4, this will be max val 2. So I need to find max val of 4. That's another recursive call. And now, if I put in a book, that's 1 plus 2 pounds left. If I put in a phone, that's 9 plus 1 pound left. And if I put in a tablet, that's worth 13 plus 0 pounds left. And there's a base case built into this, which is if none of my items fit in the bag, and if my capacity is 0, none of my items are going to fit, I'm just going to return this initial value, which will be 0. So max val of 0, I'm not going to have to do any calculations, any recursive calls. I'm going to basically do a for loop that never does anything. And I could put an explicit in here, if capacity equals 0, return 0. But that's the effect of this loop. So here's one function call I'm not going to have to recurse on, right? But I'm not there yet. I got to find max val of 2. So that's another recursive call. My stack is getting full over here on the side. So capacity of 2. All right, so here things get interesting. If we put in a book that weighs 1 pound, or it has a value of 1, it weighs 2 pounds, so we have max value of 0. Item 2 we cannot put into our bag because it weighs 3 pounds, our capacity is only 2. So we don't actually do anything for this calculation, we don't do anything for this calculation. But we do have to make one recursive call to max val of 0, and when we call max val of 0, remember we can just put a base case that says if capacity is 0, return 0. So max val of 0 is 0. And so if we start with item 1, the best value we can get out is 1 plus 0, that's just 1. And we've got our first answer to a max val question.
The base case in that if capacity is 0, that's just for efficiency, right? I mean, it's not gonna,
That's just for efficiency, and if we didn't have that, yeah, it wouldn't cause any problems to have capacity 0 because none of these if statements will be true. We'll never make a call to max val inside here. We'll never do this, and when we're done, best will just have its initial value, which is 0. We'll return that.
Okay.
All right, I'm going to record the inventory at this point. This was the inventory we got by putting in one of item 1. So item 1, we have one of those. And we didn't put in anything to solve max val of 0. That was a base case, so we don't have anything for item 2, item 3. And now we've got the complete solution to max val of 2. The maximum value we get is 1, and here's the inventory of items that we have. So the inventory, I'm just storing a count of how many of each item I have. So 1 book, 0 phones, 0 tablets. Gets us a value of 1. That's the most we can get out of a bag that holds 2. Now we can return...
So do you have a separate array for the inventory?
Yeah, so I have a separate array, and it can just be an array of integers. And if you have, 64 items, it's just an array of 64 integers. And the value of each integer is how many of that item you have.
So you could just do like inventory I plus plus kind of a thing.
Mm-hmm, exactly.
Okay.
And we'll see that in a little more detail as we start to pop out of our recursion. Now we got one more recursive call to make, which is max val of 1. And so capacity is 1. What's the maximum value we can get? Well, if the bag only holds 1, we can't put in the first item or the second or the third. The maximum value we get out is 0, and the inventory is all zeros. All right. So well, let's come back from max val 2 first. So we found max val of 2 was equal to 1, and the inventory was 1, 0, 0. So we're calculating max val of 4. Starting with a book, the value we get out is 1 plus max val of 2 is 1, that's 2. And the result from max val of 2 was 1 book, 0 phones, 0 tablets. Since we're starting by putting a book in, this is going to be 2 books, 0 phones, 0 tablets. All right, second iteration of this loop, 9 plus max val of 1. Max val of 1 is 0. And that comes from putting in nothing. And so our solution for starting with item 2, the phone, is 9 plus 0 is 9. And the inventory that gets us that, we'll take the inventory that maximized this and bump up the count for item 2. So just increment this to a 1. And then the third case, start with the phone, item 3, max val of 0 is 0. And a bag that holds 0, the solution is, don't put in any items. 13 plus 0, this will give us 13. And the inventory that gets us this is the inventory we got from this, 3 zeros, but we bump up item 3's count by 1, so change this to a 1. All right, what's the maximum value? It looks like a 13 right here. So the max value is 13, and the inventory that gets us that, 0, 0, 1. All of that, it was the first pass through our for loop in trying to find max val of 6. So max val of 4 is 13, and the inventory that gives us that is 0, 0, 1. And so in the case where we start with a book, the best value we can get is 1 plus 13 is 14. And the inventory is the inventory from max val 4, but we bump up the count of item 1 by 1. Everybody see the process we're doing here?
So to increment the inventory in the array, would you just do a series of if statements, like if the value that you're adding to the recursive statement is 1, then increment this one, or...
Yeah, so as you go through this loop, every time that you find an item that's giving you your best value, right? Just remember what the index of that item is, so best index equals I. So if I get to item 1 and this turns out to be a better value than what I've seen so far, remember that best value, and remember it was item 1 that gave me that best value. And then at the end, I can just increment my inventory bracket best index. That's one way to do it.
Okay.
All right. We are almost done with recursive calls. Not quite. All right. We need max val of 3. I don't think we've done max val of 3 yet. I've got more call frames available. All right. So let's do a recursive call to max val of 3. So capacity 3. We can start with a book. It has a value of 1, leaves us with a capacity of 1. We can go with a phone, has a value of 9, leaves us with a capacity of 0. We cannot do a tablet. Max val of 0 has an inventory of all zeros, but since we're adding item 2, we'll change this to a 1. Max val of 1 has an inventory of zeros, but since we're starting with item 1, we'll bump that up. Max val of 1 is 0, max val of 0 is 0. We've done those before. Right, those were over here. And so 1 plus 0 is 1, 9 plus 0 is 9. So this is the way we maximize the value for a bag with capacity 3. Put in a phone. I mean, we can see that, but the computer can't. But it'll find the same answer. So max val for capacity of 3 is 9, and the inventory is 0, 1, 0. So no books, 1 phone, no tablets. All right, we return from that call. Now we know max val of 3 is 9, and the inventory is 0, 1, 0. 9 plus 9 tells us we get 18 if we start with item 2, and we bump up the count of item 2. And then the third possibility is 13 plus max val 2. Well, max val of 2 is 1, and the inventory is 1, 0, 0. So 13 plus max val 2, 13 plus 1 is 14. And we're bumping up 1 extra item 3, so this becomes a 1. Well, our 3 possibilities, 14, 18, 14, this looks like our best solution. So max val of 6 will be equal to 18. And the way we get that is 0, 2, 0. And that is our first iteration of this for loop. Right, this is why we have computers. So max val of 6 is 18, and the inventory is 0, 2, 0. And 1 plus 18 is 19. And we bump up item 1. Alright, we've not done max val of 5. You getting the idea of this? We don't necessarily have to finish it. Let's just finish for a capacity of 8. Well, 8's going to be a pretty easy case. But we've done max val of 6, right? and we got a non-greedy solution. The best option for a capacity of 6 is to put in 2 phones. All right, and we've violated our greediness. Our greediness is to say, well, let's put in a tablet because that's most valuable. Best solution for 6: no tablets, no books, just 2 phones, and it gets us a value of 18. So we can keep doing this, and we can work up, to our original case and find max val of 5 and 4. Use that to calculate max val 8, and then do the same kind of thing for 7 and the same kind of thing for 6. And when we're done, we'd find, $31. But we've done enough of this for you to see something that's happening. We keep recalculating the same values again and again. Now over here, when I need max val of 4, I'm just going to go to my worksheet where I calculated a max val of 4 and say, oh, it's 13, here's the inventory. But the poor computer, if we just wrote this code, every time that we wanted to do max val of 4, we would go through all 3 of these steps. And this one would involve calculating max val of 2, which would be this other set of steps. And the amount of work that you're doing is huge because you're replicating the work so much. And so the dynamic programming part is, writing down these answers as we calculate them. Once I know max val of 6 is 18 and this is the inventory, I'm going to cache that. I'm going to save it somewhere in memory. And then later on, if I need a max val of 6, I'm not going to do all of this stuff. I'm just going to go to my memory and say, oh yeah, that's 18, here's the inventory. So I'm just going to read it out of there. So that's the dynamic programming piece. So this is the recursive structure, right? And the repeated subcases is, max val 6, max val 6. Gets done multiple times. If we tried to do max val of 1,000, we would find ourselves, calculating max val of 8 a ridiculous number of times. And max val of 9 and max val of 10 and all these other values. So we save those in memory, and it curtails having to do these recursive calls too many times. All right, questions about that part of it?
As far as the saving part, the computer is saving it while it's running in the for loop, or we're doing something special? I think I missed that part.
So all you're going to have to do, and when I say all, I don't mean it's easy, but all you're going to have to do is in the beginning of your max val function, see if you've already calculated max val for that capacity. So an array of integers perhaps, indexed by capacity, and if you've calculated the max val for that given capacity, that entry in the array should be bigger than or equal to 0. So maybe initialize your array to -1. And so check to see if element cap in your array is -1. If it is, this is the first time you're calculating this capacity. Go ahead and do all this work. And then at the end, save bracket capacity equals best. And so in the beginning, if save bracket capacity is not equal to -1, you can just return that.
So you don't have to do any appending or anything like that. It just saves to that.
Yeah, just stick it in memory somewhere and then pull it out.
So you want to initialize the array to be something ridiculous then?
Yeah, set it to something. You could probably get away with 0 without too much issue, but certainly cleaner if you initialize it to say -1. Because we know the capacity, the max val should never be negative.
Oh,
And so-
I see what you're saying. So if it's -1, then it's obviously an empty array. There's nothing in there, right?
Right.
Okay, gotcha.
And so with the inventory, you can have parallel arrays, or like I say, you can make a structure, and your structure could contain, for each item, the name, the weight, and the value. And then you can use that in creating a memory cache. And your memory cache would contain, you know, for a given capacity, the maximum value, and also an inventory, so an array of how many times each item should occur. And you can make that thing a structure, right? Make a new structure that contains a capacity, or sorry, a maximum value and an inventory. And now your save array is just an array of this, you know, struct answer, for example. And you can make a loop to initialize a flag in there if you want, saying, you know, is this a valid entry in the cache or not? So there's flexibility about how to go about implementing this. But that's the mechanics of how we're going to do this, how we're going to track the inventory. And, you know, we get the inventory from MaxVal, so we know if we want a maximum value from a 6-pound bag, this is, you know, the combination of things. And so this solution is whatever you do to get that max value plus one more of item 1. That's that bumping up, you know, item 1 or item 2 or item 3. So the highest level concept, not too bad, right? But the details are pretty complex. And so this is another example of a program that you're going to want to think about and sort of, you know, organize on paper and in your head before you do too much coding. The actual coding is of the MaxVal function is not much more than this. But the logistics of you know, how am I going to store the weights and the values, and how am I going to store my cache and that kind of thing, that's where a lot of the work will be. All right,
Yeah,
so
I could see if we've already cached that specific index or that specific capacity, we'll have to somehow call a way to increment the inventory, right?
Right. Yeah, so as you go through this loop, you're going to keep track of what the best inventory is. Right, you're going to get an inventory from MaxVal each time, and if you've got your best value, you need to remember what that best inventory was that got you that best value. And then bump up, you know, whatever your index was in that loop, bump up the count of that item by 1.
So if we stored that in a structure, then we can do that inside the structure,
Mhm.
right? Have that.
Yeah, and making good choices about what kind of structures you want will make a big difference in the feasibility of getting this to work. Because it's a lot of information, but a lot of it belongs sort of logically together with other pieces of it. We want a way to remember, you know, this thing gave us a certain value. This is the resulting value we got from that combination. If that was the best, well, let's remember what the best value is. Let's also remember what the combination of items was that gave us that. So we need a way to get the combination of items that gives us this max value so that we can bump up, you know, the count of item I, and remember that so that at the very end, when we exit, we know not only the best value, but we know the inventory as well. We need a way to return that to whoever called MaxVal, and we need a way to save that in our cache.
And so the output of this is just going to be, you put in a command line argument with the database and how big you want it, and it should just return a value for the number plus the inventory.
Yeah, so let's look at the actual assignment and see these kinds of details. So you're writing an executable program called knapsack, and it takes 2 arguments: capacity of the bag and the name of an inventory file. All right, the inventory file contains lines with triples as follows: a name, value, and a weight. So, you know, for this, it would be book 2-1, phone 3-9, tablet 4-13. But it can be, you know, whatever somebody wants, within reason, right? So there's no spaces inside the name because that makes parsing really hard. So it's just a name, which can be any string of characters, a space, and then the value of that item, a space, and then the weight of that item. And all of these are going to be integers, so we don't have, 2.5 pounds or something like that. And, there might be 4 things in here, there might be 40 things in here, so you read until you get to the end of the file, build up an array in memory. And then echo the contents of the file, so print that out in the beginning, and then calculate the maximum value. And at the end, print out the maximum value along with how much of each item gets you that value. All right. Again, I recommend making good use of structures here. You definitely need to use dynamic programming. Otherwise, this thing for large files will just sit there and churn for hours. And so here's a good sample output, right? I'm running, and this is available on the server. This sample executable and a sample item file. And so if I run this with a capacity of 21, first thing it does is print out a copy of the inventory file. So weight, value, name, right? Print it out here. And then tell me what the bag's capacity is, right? 21, which is just that argument. Tell me what the maximum value is, and tell me how much of each item I should use to get that value. And so think of this as just kind of, a report on the solution to this particular problem. So yeah, I know it's 21 pounds because I put 21 in the argument, right? But go ahead and tell me the capacity is 21. Tell me what the maximum value is. Tell me how many of each item. So here's a sample file, and there's a sample executable. So if I say, the capacity is 100, and here's the data file, it'll tell me, hey, the maximum value is 400, and it comes from putting in 20 phones. If I do 10, it'll tell me the solution is there. So, So let's do our inventory file. So a book weighs 2 pounds and is worth 1. A phone weighs 3 pounds and is worth 9. And a tablet weighs 4 pounds and is worth 13. Ooh, I messed up. My N key is like gotten bouncy on my keyboard.
It makes you feel better. I feel so on the keyboard the other day.
Oh no. That's a bad one.
You could do the old keyboard in the dishwasher trick.
Oh, have you done that?
Yes, I have.
Does it work?
Works surprisingly well as long as you just let it dry.
Okay.
For most keyboards, I would say.
I was going to suggest distilled water, but dishwasher sounds more profound. All right, so let's try the knapsack problem with 10 pounds on this sample file, and there's your solution: 1 tablet, 2 phones, maximum value 31. So you're welcome to use this sample executable and use it to find the solution to different database files, and then compare that to the answers that you're coming up with, and that can help you tell if you're getting the correct answer or not. There's not a whole lot of other detail in the assignment prompt. So program behavior, we've discussed the algorithm in class, so that's the algorithm you want to use. But here's a synopsis of it, right? Max val x works by returning 0 if x is less than or equal to 0. Otherwise, return the maximum of value 0 plus max val x minus weight 0, value 1 plus max val x minus weight 1, and so on for each item. Computed over all items where the weight is less than or equal to the capacity of the bag. Print out how many of each item gets you that value, so keep track of the maximum value as well as keep track of the solution that gets you that. Use dynamic programming, so save things in the beginning, save things at the end, check things in the beginning. so that you don't recurse needlessly. Error checking, basically make sure you've got two arguments, make sure the first one's an integer. So basic sanity checking, make sure you can open the file and don't just throw up, right? So if they give you an inventory file that you can't open, you should notice that and say, you know, bad file or something like that. Simplifying assumptions, you can assume a maximum of 128 items in the item file, which means that if you're using, you know, some sort of arrays to store this information, you can declare those to be arrays of, say, 128. So you don't need to dynamically allocate space for those, because we know there's never going to be more than 128 items. Maximum bag capacity is 1024. Why is that important? Because dynamic programming, we're going to save answers in a memory cache. Well, if we use the capacity of the bag as our index and the biggest capacity is 1024, at most we need, you know, 1025 elements in our cache. So that can be defined as a fixed size array. We don't need to dynamically allocate space. And you can assume that each name has a maximum of 32 characters, no spaces. And so the names can just be, you know, car bracket 33, 32 characters and an all terminator. So I don't think you have any need to do mallocs anywhere in here. Everything can be statically declared, so no memory leaks.
So if we're doing like a structure, we don't have to malloc for a structure?
You shouldn't have to. If you have to, that's fine, but I don't think there's a need for that because I think our structures can be defined, you know, as, you know, struct whatever variable name, which allocates space for it, and then if you want its address, you can do, you know, ampersand variable name. But if you prefer, you could make your variables pointers to structures, and then you'd want to use malloc to grab space for them, and then you'd want to free those at the end.
And then you can do pretty much an array of anything, right? You should be able to do an array of structures.
Absolutely.
Can you do that?
Yep.
How would you start something like that?
What do you mean start?
Like how would you initialize that?
So like, you know, struct item bracket, struct item, item list bracket 128. Right, that's an array of 128 struct items. And then I could say, you know,
whatever a struct item is.
yeah, item list bracket I dot, you know, name dot weight, etc. And remember, if it's not a pointer, if this is actually a struct item, you use a dot to indicate the field that you want to access. So those arrows are only if this is actually a pointer to a structure.
So would you recommend, if we do it that way, put some kind of way to increment the capacity, or not capacity, but like how many we're using for the value inside the structure, or should that be a separate array thing?
It depends which structure, but yeah, I think there's structures where you could put that inside.
Okay.
One thing to keep in mind is do you want one copy of something or do you want multiple copies of something? So you know, if I need to return an inventory from here and I'm trying to keep track of the best inventory that I have in this for loop, that might just be one inventory array, right? I don't need to keep track of multiple ones. But in my cache, right, I'm going to have a whole array of different capacities, and for each capacity, I have a max val, which is an int, but then I have an array of, you know, how many of each item corresponds to that maximum value. And so thinking about, you know, do I want just one of these? Do I want multiple of these? Can help you decide, like, should this be a structure? Should it just be an array of ints? That kind of thing.
Okay.
All right, so simplifying assumptions, take advantage of those, make life as easy as possible. Submission, just pi5.tar, uploaded to Canvas. And originally the due date was set for a week from Monday. I moved it back one day, so it's a week from Tuesday. So whatever day that is, I believe
That'd be,
that's
like,
the
not
8th.
next week, but the week after?
So not the 1st, but the 8th.
Yeah. Okay.
Yeah. So it's you know, almost 2 weeks from today. And then grading, really straightforward, right? If there's no upload, you don't get a point. If it does not compile, it's at least 50 off. If there's warnings, it's 10 off, right? Seg faults, 50 off. If it does not give me a solution, that's 50 off. So, you know, you're going to know what your grade is pretty much, right? If you can run this thing with an inventory file and a capacity, and you get a solution and it compiles and so on, right? Don't worry about these. But you want to get an optimal solution. And so compare your answers to the sample executable. And that'll tell you if you're doing the right thing. But even if you get the wrong answer, right, you can still get 70 points out of 100 by simply not seg faulting, by compiling correctly, and so on and so forth. But, you know, try to get the optimal answer. Make sure you're using dynamic programming. So what is a short amount of time? Until I get bored, okay? So if you do dynamic programming, this should come back right away, right? If it doesn't come back right away, I might wait, you know, 10 or 15 seconds. But certainly if it hasn't come back after a minute, I'm going to say it doesn't run in a short amount of time. And you'll know when you run test cases, do something with, you know, 20 items and a capacity of, you know, a few hundred or something, and it should come back quickly. If the inventory is not correct or it's not present, that's 15 points off. So if you can't get the inventory to work, but you get everything else working, you can still get an 85, right? So the inventory is kind of like the delete function for PA4. It's something to sort of keep in mind and then try to get together at the end, but it's not a make or break for the whole assignment. But it is a trickier piece of it, on par with, you know, deleting from PA4. So if you get the correct inventory, right item counts, that gets you 15 points. If not, then that's just one deduction. Yeah.
Regarding, I just remembered I had a question about PA3 that's very similar to what you just said.
Mhm.
For some reason, my type function, when I put in a full database, takes like a second or more. It's not quite as instantaneous as the one on the server. Would I lose any points potentially for that?
No, but I'm curious why it would be slow.
Yeah, I was curious too.
Is it
I'll look
recursive?
into it. It's recursive, yeah. It's
Okay.
just a little bit slower. Could be my
Interesting.
machine, I don't know.
Yeah, let me know if you find it, or if I notice it, I'll let you know. But
Okay.
yeah, for PA4, if there's just some reason why it's slow, that's okay. But if it's because you're doing something really bizarre, then I'll dig into that.
Okay.
Is there a specific name you want for this one? Did we talk about that? Can you talk about that?
So the executable should be called knapsack.
Knapsack.
Yeah. And again, I don't have it in here, but I also want you to make a make file that's on the Canvas page where the assignment is listed. Just include a make file so I can say make and it'll build this, or I can say make clean and it gets rid of the made stuff. And that's pretty much it for PA5. And it goes without saying that this is not something to try to do in one day. But I just said it, so it goes with saying. It's you know, it's a different kind of challenge from PA4. PA4 is you know, a lot of functions with a lot of recursion, but the functions themselves are generally pretty small, other than delete, right? Delete's just a monster. But PA5 is you know, really one function, maxval, that's going to do everything, and it's going to have a lot of stuff going on inside. It's going to do, you know, not only this looping and checking for edge cases where you can't fit an item, and keeping track of the maximum value, keeping track of the inventory, using a cache in the beginning and the end. It's like all this stuff thrown into like just one poor little function called maxval. So it's a different kind of challenge from some of these other assignments. It's interesting. And these problems don't always the solutions don't always jump out at you, right? For a capacity of 1,000, right, your best answer was 250 tablets. For 1 pound more, you're better off giving up 2 tablets and adding 3 phones, and you get an extra $1 out of your capacity. And it's because these things don't have obvious solutions that we end up with, you know, recursive approaches like this to finding a solution.
It seems like this is a little more rare of a thing you'd have to do with recursion, right?
It's a fairly common use case, actually.
Okay.
And you can hop online.
Watch a lot of computer file, and they're usually like, oops are almost always preferable until you hit certain problems.
Yeah. So like you can find lots of pages like top 20 dynamic programming interview questions, right? So we're doing a 0-1 knapsack problem, and we're going to talk about rod cutting.
Page,
Say again?
paste that whole page, please.
I'll put the link in chat.
Thank you.
Yeah, but it was just a Google on like I Google dynamic programming problems. So there's the top 10, there's the top 20. So we're going to talk about some of these next week. We're definitely going to talk about rod cutting because that's a really simple example. We'll talk about egg dropping, which is a fairly complex example, but another instance of this recursive substructure and repeated subcases. And we'll probably talk about longest common subsequence because that's a really common situation also. But all of these, you know, basically break down to the same kind of thing where we're trying to write a function and we can describe it in terms of the same function evaluated at, you know, simpler problems, smaller arguments, for example. And that's just a classic application of this. Other questions?
So saving an array of integers, should we use a pointer to an array?
Well, that's a loaded question because arrays actually are pointers.
That's what I thought, but I keep getting something that says you can't assign a value to there because you're making an integer from a pointer without a cast.
Let's see. So if I have, you know, something like integer save bracket 1025, right? I can so usually for these caches we just make these global. If we're talking about the dynamic programming piece, right? We would just define this outside of your max_val function, define it before so that it's globally available. No need to make it a local variable or anything. But you know, whatever we have, if we have an array of integers, for example, if I call some function and I just pass the name of that, right, inside my function, I can define this to be an integer star. So if I say integer star arg, and then inside here I can say arg bracket some index, and it'll pick up, you know, the elements out of that as if it were an array. So when we pass the name of an array, we're actually passing the address of the first element, right? Or a pointer to an integer if this is an array of ints. And so in our function, we declare it to be a pointer, but we can use it like a plain old array, access elements with brackets and so on. All right. We've got about 10 minutes left. Let's look at this longest common subsequence question. This is a different problem, but a similar feel. So here's the question: we have a string, you know. And we've got another string. And the question is, what's the longest sequence of characters that are contained in here and in here? And so, for example, A space TES, A space TES, that's a common substring of length 5. HELLO space BY, actually with a space in the beginning, space HELLO space BY. That's a common substring of length 9. And so the question is, given two arbitrary strings, how do you find the longest string that's in common among both of them, the longest substring? And, you know, they're not going to be in the same position, right? And so this typically comes up where you're sequencing DNA, for example. So there's one strand of DNA and there's another one. And I think the longest common string is going to be this ATTACGA. Right? And that looks like it's common to both of those. But, you know, there might be other stuff before here and other stuff after here. And somewhere out here there could be, you know, some string that's even longer that also appears right here. And when you're sequencing DNA, if you have two strands, right, you'd like to put those together. Well, if I know that this string is the same as this string, then maybe I can take all of this and put it over here and get an even longer strand with all of this stuff, followed by this, followed by all of this. And so this is an algorithm that you'd be interested in when you're trying to, you know, analyze strings like this. And it's a combinationally complex problem, because how do we do this? Well, start with the first character and see if you can find that character anywhere in here. Well, if you can, you found a substring of length 1. Now take the first two characters and see if you can find those. Take the first 3 and so on. And now do the same thing, but start with the second character and find a longest string of length 1 in here, or length 2, or length 3, and so on. And again, it's a couple of nested loops. It's not too hard to write the code for that, but it takes a really long time. But there's a different way we can define that problem using recursion. So longest common substring of two strings A and B. And this should return an int. I'm just interested in the length of the longest string. So there's two possibilities. Possibility 1. If A and B end with the same character, oh, I forgot one thing. These don't have to be consecutive. right? That's the part that makes it more complex. So if one string is like and my other string is, you know, right? What I want to do is I want to say, hey, there's a T, there's an H, there's an I, there's an S, and so and there's a Y, and there's a Q. So I have two substrings of length 6, right? So that's the part that makes it really tricky, is that these strings don't have to be consecutive. So you're looking for a pattern of strings in a particular order that matches the same pattern in that order in this other string. So that's the common substrings we're looking for. So if A and B end with the same character, then we return 1 plus the maximum of the longest common substring of A prime comma B prime. This is A and B without the last character. So if you have two strings and they both end with the same character, the longest common substring between this and this will be the longest common substring between these plus 1. Because whatever string of characters we find in here that we also find in here, we know that we can also tack an X onto the end of both of those. So if A and B end with the same character, take the longest common substring of these truncated strings, right, and add 1 to that. There's no max here. And just return that. All right. The second possibility is A and B do not end with the same character. So this ends with an X and this ends with a Y. Well, now we know that whatever the longest common substring between these two strings is, it does not end, it's not going to be the case that both of these common substrings end with the last character of these strings, because X and Y are different. So in this case, we're going to return the largest of the longest common substring of A and truncated B, or the longest common substring of truncated A and B. In other words, find the longest common substring of this, and find the longest common substring of this original string and this. And whichever one of those is longest, that's the length of the longest common substring between these two strings. And what we're doing, the reason we're doing that is because for this kind of recursion to work, the recursive calls have to be in some sense simpler. We can't just call with the exact same arguments A and B because we'll recurse forever. We can't call with arguments that are going to require more recursion. We need to somehow be working down to some kind of base case. And so in this case, right, A and B are both going to be 1 character shorter. In this case, B is 1 character shorter. In this case, A is 1 character shorter. And our base case is if A is empty or B is empty, so if their lengths are equal to 0, then there's no substring at all in one of those, and so the length of the longest common substring is 0. So we can code this, and I don't have dynamic programming in here, so it'll be slow on long strings, but you know, I'm going to enter 2 strings. I'm going to chop off the new lines because I don't want those. I'm going to call LCS, longest common substring of each string. I'm going to pass the number of characters in the string, because to truncate a string, I'll just subtract 1 from the length I pass. And here's the whole LCS algorithm. So I'm going to print out, you know, what the strings are that I'm trying to calculate. If either one has a length less than or equal to 0, just return a 0. That's our base case, gets us out of the recursion. Otherwise, I'll echo, and then I'll see, do both of these strings have the same last character? If they do, I'll take the length of the longest common subsequence of the sub-truncated strings, add 1, and return that. Otherwise, the last characters differ, so I'll call LCS twice. I'll call it with A and truncated B, and I'll call it with truncated A and original B, and I'll save those two values. I'll return whichever one is larger. And then this is just my print function, so I can print out these strings, because I don't have null terminators on these strings necessarily. So I'm going to print out based on the length. And if I run this, here's one string, here's another string, and it does a lot of recursion. And you can see that it keeps finding, the same base cases multiple times. Well, maybe that's not obvious, but like, this one, DJHAJ and DJ or JDHAJ, right, is being called twice. It's going to be called a lot of times. And if I just run this, through a word count and put in a few strings, we'll see how many times it's recursing. So I think that's 11 million calls that it made to this this function. So without dynamic programming, this gets really slow. But the gist of it is really just this. If the two strings end with the same character, I call LCS on the truncated strings, add 1. Otherwise, I call LCS twice, truncating first string B and then string A, and I return the largest answer. And that gets me to, all of this work. And, all of that. I actually overflowed my scroll back capacity, which is 1 million. But pretty simple code in terms of the number of lines. So longest common subsequence, another classic problem. We'll take a look at rod cutting on Tuesday. That's a much simpler version of this kind of algorithm. And then we'll take a look at egg dropping a little more carefully, because that's just a fun problem to work on. And we'll see how that works, and we'll look at some code for that. All right, we're out of time here. So
Nick, I have a quick question.
Yeah, go for it.
So they just announced that Canvas is going to be closed all week. How are we going to turn in our SLP uploads?
You sure Canvas is going to be closed?
I think they said...
I don't think they can do that. I think CTC Link.
Will be unavailable.
Right,
Okay.
but they always tell you Canvas will still be available.
All right, never mind.
Okay, cool. Yeah, that would be bad. All right, cool. Have a good one. Finish up PA4. Good luck with that if you're not there yet. And I will see everybody next time.
Thank you.
See you
Hey,
next
Nick.
time. Thank
Nick,
you.
real
All right.
quick, I wanted to ask you, are we still using the same method to read from the file?
Yeah, so do an fopen, do some fgets, do an fclose.
Okay.
Yep,
'Cause
that's...
I was trying to do that. It's saying that it can't read the file format because it's .data instead of text.
Oh, no, I shouldn't care about that.
Okay, so I just kind of copied and pasted. I'm just trying to get the database inputted, and it's giving me a bunch of errors.
Yeah, C should never care what the actual file name is.
Yeah, it's in file format not recognized, treating as linker script is what it's saying.
I'm guessing that maybe you're trying to execute it or something slightly bizarre like that.
I'm just trying to compile it, GCC.
What's the name of the file you're compiling?
Main.c.
Okay.